lecture by Professor Sharma on 28th of September 22 was organized. During this period, we have organized 8 lectures by prominent speakers, including Professor Sharma, Professor G. Jerome, S.S. Ruvedi, Professor Rangan Banerjee, Professor S.S. Rao, Mr. J.S. Mukul, and latest by Professor Akhilesh Gupta. A wide variety of topics including 5G, futuristic technology, 20, and our own NSF, that is National Research Foundation, which have been covered in these lectures. Electricity is something without which we cannot think of our life. But we as a user accept electrical engineers since we as a human being witnessed the first use of electricity. Today we are here to listen to Professor Anil Pahwa about the past, present, future of electrical power distribution systems. Professor Pahwa is a prominent technocrat, educationist and administrator who had served US technical education for more than 4 decades. Professor Pahwa, speaker of the day, Professor Padi, director MNIT, my faculty colleagues, staff, dear students, a warm welcome to all of you to this lecture. I would now request Professor Padi to please welcome the speaker, Professor Pahwa, with a floral bouquet. Please, I would request Professor Pahwa and Professor Padi to please come on the dais and lighten the lamp.
You can come to everything is yours.
Thank you. Considered to be pioneer in his field of distribution system. And today we'll be talking about past, present and future of electric distribution. Considering the winter vacation, which is about to start tomorrow, I thought that most of you may not be able to join, but still I'm very happy that we have reasonable strength in the room to lecture today. Thank you, sir. Please.
So, before Professor Pahwa starts the lecture, I would like to introduce him to you. Dr. Pahwa has worked for 40 years in electrical and computer engineering department at Kansas State University, where he is presently University Distinguished Professor and holds the Logan Peterhoff Chair and the MS degree in electrical engineering from University of Maine, Orono in 1979 and the PhD degree in electrical engineering from Texas A&M University, College Station in 1983. He served as a senior scientific advisor in East Asian and Pacific Affairs Bureau of the US Department of State in 2014 to 15. He was a program director for Power and Energy at the National Science Foundation from 2018 to 20. He received the Distinguished Alumnus Award from BITS Pilani in 2014. Dr. Pahwa is a fellow of IEEE. Now I invite Professor Pahwa to deliver his lecture.
I'll try to make sure that I can tell you what we have. So here is a book that was published last year. And
Okay, thank you very much. Congratulations.
Thank you.
Thank you very much.
So I want to thank Abhi for inviting me for this lecture, and also Professor Mittal for making all the arrangements. And of course, you can see that my voice is not very good today because I was in here for a week and somewhere I must have caught some virus or something. I don't know what I did. But I hope that I can survive the time that I've been allocated for the presentation. So, but please bear with me because I cannot be very much as I want to be. but I try to do my best. So let's get started. I think this picture is a point from several years ago. Let's get started. So we'll just push the next button. Okay. So what I'm going to do is I'm going to talk about past, present, and future of electric power distribution systems. And for those of you who may or may not know what power distribution systems are, power systems are divided into three parts. One is the generation system. The second one is the transmission system. And the lowest end of the system is called the distribution system. So my work has mostly been in the distribution system, and I'm going to talk about that. So let's move on. So what I want to do is, this is an outline. I'm going to talk about a few historical milestones, and then talk about the current state of distribution systems. My presentation is more focused on US-based conditions, but they also apply to what is happening, and we'll talk about distribution systems of the future, and then look at how they, what is the connection with the smart grid, because most of you have heard about smart grid, and what are the new challenges. And then after that, I'll give you some examples of some research that we have recently conducted. So, as far as the power systems are concerned, the first grid was set up by Thomas Edison in 1882. And this was on Wall Street in Manhattan, New York. And this particular grid that he set up was the DC grid, which lighted 200 lamps for 885 customers. And it was 1 square mile. And each customer received power for 1 lamp. That's about it. And the people who were at the end of the grid, their lamp was barely able to light up. Now we move forward, and we see a lot of changes. Now the picture you see on the top left is of any big city in the US or in India, where we see a lot of lights being used. And the picture in the middle shows rooftop solar PV. Now this is a picture I took in Germany, but you can see similar things in India and anywhere else. And then we have the electric vehicles. But despite all that, what we find is that 1 million people around the world do not have access to electricity. And that deprives them of economic and educational opportunities. As far as the state of the distribution systems is concerned, the total capital investment in distribution systems is almost 40% of the entire investment in power systems, which is almost equal to generation system. The transmission systems are only about 20%. And of course, one of the things about distribution systems is that any kind of problem that takes place in the system will cause inconvenience to the consumers, because the customers are directly connected to the distribution system. So they have a very big importance in the overall scheme of things. As far as the legacy distribution systems are concerned, we have very little information from the system beyond the substation. So as far as the operation is concerned, it is based on prior knowledge and heuristics. So the operators know that the system behaves like this, so they use their own judgment to make decisions. Typically, utility is small size, unit size utility. So basically the operators of the chemical, they have the knowledge base. Now, what is there in the future? In the future, we see a lot more penetration of customer-owned solar and wind generation. We see a lot more electric vehicle ownership. We see smart meters in homes, and it's the real-time pricing of electricity. Right now we pay a fixed price, but in the future we can possibly see a real-time price of electricity. And then there are home area networks for demand management with smart appliances. We will also possibly expect some customer participation in buying and selling of electricity. So when people are putting solar panels in their homes, they generate excess electricity, they could possibly sell their electricity in the market. And of course, we are also looking at the possibility of home or community energy storage with batteries. And of course, people like you, the young generation, is more technological savvy compared to old people. So your expectations are much different. And of course, we are expecting uninterrupted power supply. Any kind of interruption is unacceptable. And we are expecting more flexibility. So what can we expect as far as the management of the system is concerned in the future? The distribution management systems, which are the computer-based systems that manage the entire system, they consist of multiple parts. SCADA, most of you must know about it, is the one that connects. So there is to be a much more capabilities of computation in the distribution management system. Also, we can expect to leverage big data. And we take decisions at the local level and transmit that information to the higher level for additional processing. So the systems are becoming more complex. And also because of integration of communication systems, cyber systems, there is an IEEE definition of that. We said that the system that enables the electric utility to remotely monitor, coordinate and operate distribution components in a real-time mode from remote locations. So this is what we share. As far as the smart grid is concerned, there are three components to it. One is information, second one is computing, and the third one is decision making. And that basically consists of measuring the information with new sensors, communicating that information with advanced communication systems, and making decisions with advanced computing. And that part is smart grid. Now, in terms of what is smart, how does smart grid link with distribution systems? We can think about it as distribution automation plus more, and that makes it smart distribution systems. Why do we want to automate the system? Because automation allows you to improve efficiency, reliability, quality, flexibility, and resiliency of the system. What can be automated? Number one thing that we checked, the electric utility companies in US and anywhere else, for isolation and restoration is the number one. It's called PRISM. Basically because if a fault takes place, the utility wants to know where the problem is and they want to fix it. Okay? So that's why this is one of the most important things. The second thing is voltage water control. Because in the distribution system, they want to make sure that customers get voltage at the right level. If you have voltage at low level, your appliances are going to go back. So like for example, the voltage is low or high, it's not proper. So voltage water control is required to manage the voltage within the power range. Now that can be done with switching capacitors or controlling the low tap changers or transformers or switching for electronic devices. The next item is feeder reconfiguration. What it means is that you can change the topology of the system by switching switches. The reason why we want to do that is to Also, we can do monitoring and control of equipment. What are the DMS capabilities? We can do worldwide optimization, because if you remember, the voltage is dependent on reactive power. If you put more reactive power in the system, the voltage increases. If you have less reactive power, the voltage decreases. So by proper management, you can optimize voltage more. We can do online flow and short circuit calculations. We can implement adaptive protection. We can do contingency analysis. What if something fails? What should be done when something fails? And then advanced fault detection and location can be done. So, advanced vehicle management. What does it mean by vehicle management? The utility companies have a fleet of vehicles that go around the field to manage the system. So by remotely monitoring with them, they can do optimal management of their routing and other things. Also, we can do dynamic de-rating of the equipment due to harmonics, and distribution operator training simulators can be implemented. Also, we noticed that there is a large penetration of customer-owned solar generation, for example. They cause a lot of issues, and for that, we have to have newer techniques for control and management. And the system can be operated as a microgrid, either in isolation with the main grid or connected to the main grid. And of course, I already talked to you about real-time pricing. What are the challenges for automation? One of the things that happens in the distribution system, I think let me see, hello, this one doesn't. Okay, so because the distribution system is so large that we have too many components, and automation means everything has to be automated, which requires us to have too many things to be controlled. And in addition to that, we have to implement micro PMU and AMI. AMI is advanced metering infrastructure, where you want to have meters in every home to manage and gather information on energy consumption. So all these things require a large amount of computation and a lot of investment, so it's not easy. Compared to transmission systems, distribution systems require more investment because we have too many components to worry about. And of course, when you have a large system, management becomes difficult because you have to communicate a lot more information, and that could create communication bottlenecks. So, looking at the rooftop PV, this is a new challenge because what happens is that rooftop PV has an issue because the output fluctuates. When the sun is shining, you have a lot of output. When the sun is not shining, the output goes down. And sometimes the clouds are moving in and out. The output is going to fluctuate. So as a result of that, the power goes back and forth. And sometimes the power can flow back into the system. So there are a lot of issues that have to be dealt with. And in particular, if you have a large penetration of solar during the middle of the day, when the sun is shining, the output is very high. So the power company has to reduce its output during the middle of the day and then pick it up again in the evening. And that causes a lot of fluctuation. It's difficult to manage. Let me show you a picture of solar variability. Now these are actually recorded data. You can see that over a month, the output is fluctuating by a big amount. For example, you see that here there is no output, here there is a lot of output, there is a lot of fluctuations here. So there is much change taking place. And that causes a lot of problems in terms of management. So what we did is we tried to look at the system with respect to effects, with respect to time. And what we find is that by doing that, you can manage the system very effectively. So in the normal operation, things are not changing very much. So what you can do is you don't need to worry about doing anything very quickly. You can wait. For example, nothing will change in 15 minutes. So you can wait for 15 minutes. But you don't need more information because things are not changing. So you don't need to gather more information. So in this case, you have an opportunity to optimize the performance of the system. On the other hand, if there is an event which is called a minor event, which would be, for example, some kind of you have minor event where some things are happening, such as fluctuation that are happening in PV. That is, you have to worry about things in 1 second to 1 minute time frame because things are changing fast. In that case, you don't worry about optimizing, but you worry about maintaining the operating limits. And in this case, you need some more information compared to the case where things are not changing. And then there's a third case where you have major events. In this case, for example, you lose connection from the grid. In that case, you have to operate the system as microgrid. In that case, you try to manage the load of the system such that you can provide services only to the essential loads. Not worry about everything. In that case, you have to worry about things happening in cycles to seconds. Okay? So, and of course, you need more information, not more information. So that's the kind of overview of how to manage a system under different time frames. Now, to give you an example, this is what we call as harmonic multi-agent system. And this fits very well with the distribution systems part of this structure. Because in the distribution system, we have a substation, then we have feeders, then we have laterals which are at the lower level that connect to the homes. So in this case, we use the holonic multi-agent system. Now the word holon actually is an interesting word because it means that it is a part of something and it has also parts in it. So it belongs with both ways. It has a upper level organization, it also has a lower level organization. So this word is basically, the way it works is that you have agents at different levels in the system. You collect information from the lowest level and you make decisions and pass the information to the higher level and you do that again and pass that information to the highest level and then the commands are transmitted from top to bottom. So this is something we call it a holonic multi-agent system because it allows to control the system in a very systematic manner. We published a paper based on this, which is also listed at the bottom. Now, we also implemented an approach called analytical targeting, target cascading method for distributed optimization. So what we did in this case is that we broke the system into 3 parts and we used the computing at each level separately. So we start from the bottom to the computation, pass the information to the next level, and then same thing to computation, pass the information to the next level, and then go from top, we go bottom, bottom, we go to the top. And then the idea is to match the boundary conditions. So when the boundary conditions become 0 or close to 0, then you start the solution. So that's what is called this is called a distributed approach for optimization. And I use that to a natural system. And what we found was that if you have to do the calculation based on optimized approach, it takes several hours to solve the problem. If you use sequential ABC, it took 355 seconds. And if you use parallel ABC, it took 118 seconds. There is a huge improvement in the time it takes to do the computation. But as far as the accuracy is concerned, the accuracy will not change very much. You're losing only a little bit in terms of accuracy. So this is a good way to solve the problem very quickly. Now let me talk about another topic, which is of advancing solar energy in rural America. Now we all know that solar energy is becoming very popular worldwide. There are a lot of things happening in India and in US also. We are seeing a lot of things happening. The only thing is that a lot of things happen in urban areas. The rural areas are kind of left out. So where are the opportunities? So we looked at the case of a small city called Greensburg, which is in the central part of Kansas. And before I talk to you a little bit more about what we did, this is a very small city. It was hit by a tornado in 2007. The entire site, this tornado is like a cyclone, but not a cyclone is come from the sea, but this is on the land. And the whole entire city was destroyed, completely destroyed. So what they did is they built the city as a community that has been built as a model community for sustainable living by putting green in green farm. So they are very much focused on urban energy, sustainability, those kind of things. And what observer described Greensburg as a unique place where rural values meet global vision. So the restored community has a population of approximately 850 people. Now you may think 850 people is less than the population of this campus. But like you have out of 5,000 students and maybe about 500 faculty and other people talk. This is a very small city, but that's very typical of US. There are a lot of small cities all over. And these cities, what they do is, they are pretty much self-sustaining. What that means is that they have their own municipal electric supply. They don't generate any electricity, but they buy electricity from a wholesaler and then they distribute it to the customers. But when they buy electricity, they have to pay for energy, which is kilowatt hours, as well as for demand, which is kilowatts. The demand is the maximum demand that happens within a month. And they have a very steep charge for that. So what we are looking for is an opportunity to implement solar energy so they can generate their own electricity to supply to their people. So before we can do that, what we did is we looked at their load profile. So this particular slide shows the load that is typically seen in the city of Greensburg in the month of January. So what you notice is that the load has a peak here in the morning because January is a very cold month. So everybody is using heating in the morning. So when people wake up, the buildings, the schools have to be warmed up, and all the other public buildings have to be warmed up. So the load is very high in the morning, and the sun shines only in the afternoon. What you see here, that's the PV output, the solar output. So what you see then, the net result is this one. What you will see here is the solar PV reduce the energy requirement, but it did not change the demand. Okay? So we cannot get the benefit of the demand part of it. Now let's look at another example, which is of same. This is July, month of July. What you notice is that in this one we have the peak in the middle of the day, and it's also high during the middle of the day. So we get some benefit. But if you look at the entire year, we really don't see a huge benefit. So we thought, okay, let's do an analysis and find out how much benefit can the utility get by implementing solar PV. And this next slide shows you the results. What you see is 4 cases. Case 1, 2, 3, 4. The energy cost as well as the peak demand charge is shown, and we considered a tax rebate of 30%, and we did the analysis for a long period of time. Only in one case it is positive, which is the case where this one. So basically, it is not beneficial for the city of Greensburg to install their home solar panels because their rate is almost close to this specification. So what we said is that if we have to make it feasible, we have to consider battery storage. Come on. Just energy savings is not good enough because you're not getting enough back. So what we said is, okay, let's implement a battery. Well, the battery is it shows the operation of the battery. Where the battery can be charged during the day when the sun is shining. So use solar energy to charge the batteries instead of trying to compensate for the load itself. Charge the batteries and then charge them in the night and in the morning. Okay? So that's the formula here. Now, if the battery is large enough, then we can, this is the charging area, this is the charging area. If the battery is not large enough, then the red line is the line where the battery cannot take any more beyond that. So we can, in that case, we cannot flatten the profile. We can try to reduce the peak load to some extent, not completely. Okay? And that's the approach we took. So we are looking at battery on a daily basis. And the problem is that even with the largest battery that you can buy, you still cannot reduce the peak load on a certain number of days. So what we are saying is that instead of trying to reduce the peak load on every day, let's focus on 95% of the day. Not worry about 100%. So if we can do 95%, and ignore the top 5%, should be okay. So what we did is we picked different battery sizes and different solar PV sizes. And I'm going to show you an example. And what you see here. Okay, this is the graph that shows that for implementing the solar PV and battery of this size, which is an example, where we chose PV of 2000 kilowatt and a battery of 4000 kilowatt hours. then we looked at the data of 3 years, actual data of 3 years, and we implemented for every day of the year the battery, and then we calculated the new peak load, and this is the graph that you get. So what we are saying is that we can create a threshold where we don't worry about anything even higher than that, but focus on adjusting the things which are below it. Okay? So, with that being the case, we drew a plot here of different battery sizes, and that's the 95% threshold. What you see is that as you increase the size of the battery, initially the threshold drops very fast and then it saturates. So what that basically tells us is that increasing the battery size beyond a certain limit is not going to give you enough benefit because the slope is not going to be very large. So basically what it tells you is that you should stop somewhere here. Because initially the benefit is much lesser than it very much. So with that being the case, we came up with a combination of different solar PV sizes and batteries, and what you see in the next graph are a few possible combinations. And here these are different battery sizes, and these are the threshold values. And what we did is we created the present. Now we have different combinations, then we can calculate the cost associated with them or the benefit. So this is the graph that you get for different combinations. But what is that? We have the graph, PV sizes here, and the benefit is there. You notice that as you increase the PV size, initially the benefit goes up and then it goes down. So basically, this point right here, that's the best option. Okay? So in this case, we have a PV size of 100 kilowatts and battery size of 3,200 kilowatt hours. And then what we did is we picked this as the best size, and then we calculated the value in terms of the present cost benefit. And this table shows you the benefits. What you see here is that this is without PV. This is the original. The amount of money that the utility company would have to pay over the period of time that we are considering. And this is just with PV, and this is with PV and battery. You notice that we have the total cost is the equipment cost is 0. And we are looking at the benefit with respect to the base case. So this is the original expense. This is the expense. Energy cost with PV. This is without PV. Notice that the energy cost is more or less the same. It did not change very much. Whereas the demand cost is this right here. It changes drastically with battery. Okay? So basically what we do is look at the total benefit. If you were to just put PV, then the utility company is losing money, which is the loss of we have a loss of 190,000, but with PV and battery, we get a benefit of 840,000. So what it tells you is that by judicious selection of batteries, you can increase the value of solar PV, and particularly in cases where charge in addition to the energy charge, which is typical in many cases. So we also did a market color simulation. We found out that the benefit has a range which is from 800,000 to 825,000, which is tells you that the approach that we have used is robust. And anyway, now we will conclude what I talked about is that the distribution systems are becoming more complex, and we have increased reliance on information and cyber technology, and we see that there is a lot of distributed PV integration taking place in the system. A lot of electric vehicles are being integrated, and we also are possibly going to see real-time pricing of electricity, and we are leveraging smart meters for real-time system operation. Right now, the smart meters are not used for real-time operation. They are used mostly for metering purposes. But in the future, we can expect them to be used for real-time operation. And in summary, there are many opportunities, there are exciting opportunities in the distribution systems to make a difference. So you are all young people, and you have a lot of opportunities to think about the future. Here is a picture of the book that I gave to Dr. Professor Pali. This was published last year, almost about a year ago, and this is a book dedicated on the subject of electric power and energy distribution systems. And that's my presentation. I apologize for my voice being not cooperating with me, but I hope you are able to understand.
Please. There are a lot of electrical engineers here doing their PhDs. They must be curious to know something more about what has been discussed.
Any questions? Well, let me ask. How many of you are electrical engineers? Can you raise your hand? There's quite a few. Anybody working in distribution systems? No. Okay. Any questions? Yeah. Yes.
Sir, on one slide, sir, you have shown, सर जैसे एक स्लाइड पे 30% टैक्स, सर जैसे प्राइस इंक्रीज हो रहा है तो ये टैक्स रिबेट ये सेम कैसे सकते हैं सर, ये थोड़ा कैन यू एक्सप्लेन अबाउट दिस टैक्स?
Yeah. You have to buy solar panels.
Yes.
Then whatever the cost is, it can be for home use or for a business or any other location. Whatever the cost is, the government will give you subsidy of 30%. The reason why they want to do that is because they want to promote solar energy. So they want to give you a rebate. That's the only. Because without the rebate, it becomes more expensive. So to promote, they are giving rebate. Any other question?
Actually, there are lots of resources. Is there any opportunities for biofuels or any such kind
You
of?
can speak little louder. So there, speak little louder.
Integrated analysis, so we can.
Biofuels. Why we have not gone to biofuels?
Is there any geographical reason to take this particular section like that particular location?
There are possibilities of biofuels also, or hydrogen is becoming.
Nowadays, too much advancements are taking place in such.
Right. Yeah, but the point is that our focus was on typically solar because so we focused on solar only. But similar analysis can be done for biofuels or hydrogen and things like that. So, but hydrogen, I think biofuels is a possibility. Hydrogen is also a possibility.
Like
Similar You can use
Like
similar.
bioethanol and other resources which are currently being utilized in large scales.
That's right.
Thank you, sir.
Yeah, this is an example. You can use similar analysis to do the calculation for other output.
Thank you.
सर आपने वो काफी बैटरी के साइज बताई ना सर 1 किलोवाट में
Oh, yeah.
हाँ सर ये बैटरीज होती है ना सर, ये एनर्जी सोर्स के साथ होती है ना, जैसे पावर प्लांट्स के साथ ही होती हैं कि या फिर ये अलग से सेपरेट होती हैं सर? कहाँ पे इंस्टॉल होती हैं सर इनके बारे में?
Is that what you're talking about? Or you're not?
His question is, I mean, do we keep these batteries very near to, megawatt scale thermal power plants or something, which is not true.
No.
Probably it is a very low kilowatt level distribution sized batteries.
Near to the customer.
Yeah, near to the
Yeah,
customer.
because-
Or substation.
Because this city that I talked to you about, Greensburg, their total load is, peak load is about 3 megawatts. It's a very small city operated in that.
पावर स्टेशन सर?
Power station, no. We don't keep megawatt, use 100 megawatt on it, no.
No, this is not a utility scale. We're talking about small scale. So the point is that whatever the fluctuations are taking place in the load, I'll show you an example. Right here. Notice that in January,
ये
the peak load is 5 megawatts for the entire city.
ये सर
So we cannot talk about very big, because the problem is what will you do of the excess energy that you generate? So you have to have a capacity which is optimum for the load that is given.
सर जैसे ये बैटरी साइज सर अबाउट 500-600 किलोवाट्स सर यू हैव शोन इन सम स्लाइड्स सर.
Yeah. So you have
Yes.
different combinations.
Sir, where these batteries are installed, sir? Means ये बैटरी कहाँ पे है सर? ये अपने घर में होती है या फिर पावर स्टेशन में होती है?
ये power station में
पावर स्टेशन में.
this is something for the distributor. The city is the one which is going to put it. Let's say, for example, they put solar panels where, so they'll put batteries like that, not in your home. So they will have to locate it right there. Maybe at a substation or something like that.
ठीक है सर.
Or maybe our MNIT campus, we have, let's say, 1 megawatt of rooftop solar, and we can have actually 200 kilowatt hours of battery.
Right.
So probably in a campus scale we can visualize it.
Right, exactly. So this is something, this technique can be used for a small city or small campus.
That's
That's what it is. You pay for energy and demand or just energy?
We pay for energy.
More demand.
Yeah.
So in this case, this analysis would work.
That's correct. But we have an option to exchange our renewable energy. Whatever we generate, that will be deducted from our monthly consumption.
Right.
So it is something like it's a hot cake for us. Whatever PV generation we make, we get.
I think because you are a government organization, so you can only charge for energy, not for power. But I think a private organization might have both options.
That's right.
It's better to have batteries and PV or just PV.
Yes. And our PV installation is less than 20% of the peak demand.
That's right.
So we are easily consuming all the energy that is
Exactly.
needed.
You don't need to worry about it.
That's correct. Storage and other things.
But this is meant for small organizations which have not very high load. Because this in USA, there are hundreds of cities involved, which are 500, 600. Any other you pick the PV size, and then you go to a kind of like a operation, you pick different sizes of, and then you pick the one that gives you the best combination. So we are not doing any optimization in this one in terms of what you call it the mathematical optimization is more of a heuristic approach, a search approach. Brute force, yeah.
Sir, in smart distribution, one of the aspects that is related to the prediction of the faults. But if we consider from the cyber security perspective, so is it something that we can predict the cyber attacks, or is it still a hypothetical concept? Is it practically possible? If we consider the cyber security perspective, then is it possible to predict the cyber attacks, or is it still a hypothetical concept? Hypothetical concept, or is it really practical?
But you cannot predict cyber attacks, because how do you know? You can think about what are the possible attacks that you can implement, and then have a defense or a
Actually, that is the existing study. That is, we are detecting, we are mitigating, we are classifying. But what about the cyber attack predictions? Is it possible, or it is a hypothetical concept?
to predict cyber attacks.
Yes, actually I heard in one guest lecture they are working on the cyber attack prediction, but I am not sure whether it is a hypothetical concept they are proposing or actual work is going on, because I could not find any paper on the attack.
That's a good point. Because I am hearing it for the first time that you can predict cyber attacks.
Even I could not find any paper on the attack predictions, but in one guest lecture they are saying they are working on the attack prediction. But I just want to know, is it hypothetical, or we can do it?
Well, actually, what they might be thinking of is to monitor certain signatures and possibly predict if there's something happening which is abnormal, whether it's actually part of an abnormal operation or something is happening. Like you can think about cyber attack as a binary, that no attack versus attack. But this could be attack at different levels which can accelerate over time. So maybe they can monitor at the early stages and see something is going on. That could be, I think, in my opinion, possible. That, I don't know the whole lot, but I'm thinking that that could be the possibility.
Table. Now the PV sizes keep on increasing, 400, 800, 1200. But unfortunately the battery size kilowatt hour is not so smooth or linearly increasing, it is oscillating.
Right.
So why it is
Well,
oscillating?
actually, that's because of the PV size, and then, you're right.
Because normally what we do, if the PV size is more, then we put more batteries because just to meet out the peak. The pattern is almost same. But in this case, probably what I could see, the energy which is keep on oscillating, but I could see the kilowatt which is keep on reducing. Probably is there any...
Our goal is to reduce the peak load. So when the PV is very small, you need a big battery to be able to do that. And then on the other hand, when the PV becomes too large, then the battery size does not increase in proportion. Because what happens is that even though you may put a big battery, but it doesn't create any impact. For example, the battery, the relative impact is reduced, is not there. Initially, you see a big drop, but then later on it doesn't. So what happens is that if you have a very large PV, then it does not really, the battery doesn't impact much. But in between, you have a sweet spot. So you can use,
Okay.
you can get a bigger, for example, the middle part here. You have bigger battery.
Okay.
Because what we are looking for is a battery size which will
Wind power plant, then we need huge batteries. But if you have 1,000 wind power plants, probably no batteries required, but they act as a plant. I mean, even with oscillations, as a cumulative, they give a constant output. Probably, I have to read your article and try to
We are
understand.
kind of like that 95% of the days. We know for sure that even if you put a very big battery, 5% of the days we will never be able to do anything. So if you find a threshold which takes care of 95% of the day, that's the sweet spot right there. So what happens is that that sweet spot actually is such that for very small PV, you need a big battery, but as you increase the size of the PV, the battery size drops a little bit, and then it goes back up again. It is not uniform.
Correct. So if you don't mind, you can share those PPTs as a PDF version. We'll try to read it during free times.
We have to make a progression on this.
Sure.
We'll give you more details.
Sure. Thank you. Thank you.
Are greatly benefited by having an in-depth discussion on power distribution. Now I request Director Sir to please present the memento to Professor Pahwa.
Once again, thank you for coming to
First, I would like to thank the speaker of the day, Professor Pahwa, for sparing valuable time for his India visit for lecture. My sincere thanks are due to Professor Padi for extending moral and administrative support for the lecture. A lecture cannot take place without the audience. So I sincerely thank the faculty and students for being here and their patient listening. Organizing an event like this is difficult without student volunteers, and this vote of thanks would be incomplete without thanking them. To this end, I would like to thank especially Jitesh Sharma. There are many students who have been involved in this, but I would like to especially thank Jitesh Sharma and Anil who have been working for success of this lecture. Thank you all again.
It's not helping us much.
Yeah.
Were you able to hear me?
Definitely, sir. It was very interesting.
I survived, so that's good.
Thank you. Thank you once again. Okay. Please.
तो उसमें भी बैटरीज वगैरह का बैकअप रखना पड़ता है। हम भी नहीं रखते हुए ना सर, मीन्स कोई भी विंड एनर्जी के लिए सर बैटरीज का बैकअप सही है।
नहीं वो बैटरी बैकअप नहीं क्योंकि उनके पास और भी रिसोर्स है उनके सिस्टम में। It's a very big company. There are multiple resources. The wind is one of them. They have many of them. So battery is there only if you have a very small operation, then you don't have any other backup. But they have backup for gas, other
इसके अलावा सर जैसे हाइड्रो पावर प्लांट या फिर थर्मल पावर प्लांट से जो इलेक्ट्रिसिटी आती है सर डायरेक्ट, जैसे किसी भी सीट में जैसे अब लाइट है सर, इलेक्ट्रिसिटी है इंस्टेंटेनियस। ठीक है सर, थैंक यू।